Okay, so as I said, I mean, in the introductory part itself, that this course will be focused mostly towards amplifier design. But even before going into this amplifier design business, let me start off with a very basic need. That is, as I said, that you require power management circuits for any application, right? You can, without a DC source, almost nothing will work. So, which essentially means that you need to derive. Okay, by the way, even if I take a step back, why do you require a DC source? Pardon? For biasing, right? So let's assume that you don't want to, for some reason you have found out some awesome circuit which doesn't require biasing. Would you require a DC source? What is meant by to energize a circuit? Okay. So essentially, what he is alluding to is the fact that ultimately you are making a circuit to drive something, right? If you don't want to drive anything, why do you need to make a circuit in the first place, right? So, and which essentially means that you need to get power from somewhere, right? So you might be driving a 1 kilo ohm resistor, you might be driving a 1 ohm resistor, you might be driving a 1 mega ohm resistor, I don't know what. But for whatever it is, you require some current to flow into that load. So if you do not have a DC source, from where will that current come from? That is the first requirement, right? One might say that it can come from signal. Sometimes it does, but it might not be good enough, right? So in that case, you require a DC source. So typically you have the fixed DC sources in the, that you can buy 3.3 volt batteries, 5 volt batteries. If you are in high voltage, you can get even higher voltages. So the main moot point here is that you cannot really get any desired value of DC source as you want. If I want, let's say I want 0.95 volts, you cannot go to the market and get a 0.95 volts battery. Okay, so let's assume you have some battery of 3 volt. Okay, for some reason I want a 1.5 volt output, right, from the battery. What should I do? Resistor divider, right? So R this is 1.5 volt. Okay. So now, as I said, that we just don't do this for, just like that. We would like to drive something. Okay. So let's assume that I have a 1 kilo ohm load that I want to drive. Okay. So if I connect these two together, what will happen to the output? Can't hear. It will go up, down. It will go down, right? Because now you are drawing initially the current here. If this was I0, this was I0 initially. Now you will be drawing some extra current this side, delta I. Also, this current will also change to some extent, right? So let's say delta I1. But the moot point is that the resistance looking down has increased or gone up with respect to the case when I didn't have the load. It has decreased, right? It has decreased, which means this resistor divider is no longer 50-50, right? So this has gone down. Now, one might say that, okay, let me ask you, instead of giving you the answer, what can I do to restore it back to 1.5 volt? We'll see, we'll go to buffer. But let's say I don't know anything about buffer and all. From this, what can I do? Okay, let me hear from somebody this side. Louder. Can't hear. Somebody said low resistor. Where? From the top, right? Here. The idea is essentially to make it symmetric again with respect to, again, restore that 50-50 balance, right? But this will work. Definitely this will work. But the issue is that, I mean, if you take the example of your cell phone, sometimes you are calling, sometimes you are watching YouTube, sometimes you are doing video call and so on, right? Which means that, and also from your experience, you will see that, I mean, each of these activities drains your battery in a different way. Okay, so if you have your Wi-Fi turned off, you might last your, I mean, your cell phone might go without charging for a couple of days. If you have Wi-Fi turned on, then twice a day, or if you do video call, I don't know, maybe in a couple of hours or so, you have to recharge, which essentially means that this is variable. You are drawing different levels of current at under different load conditions, which essentially means that you'll have to devise some way of modulating this voltage, this resistor, and this resistor has to be modulated based on how this load is changing, right? So you cannot, essentially, what I'm trying to get at here is that in order to get this 50-50 voltage division under all load condition, you need an a priori information of the load. Somebody needs to tell you that, okay, I am going to do this. This is the exact amount of current that I will be drawing. You change your resistor. Yes. Okay. So you can use Zener diode. So what is essentially what is the crux of a Zener diode? Right. Exactly. So the Zener diode essentially is a simulation of a voltage source. Right. So I'm coming to that. So Zener diode is a very good option. But again, I mean, the issue with Zener diode is twofold. One, it's very difficult to make Zener diodes on chip. Okay, and number two is, again, the voltage at which Zener diode trips is also not very programmable. Right? If I mean, here I took the example of 1.5 volt. It can be 0.9 volt. The requirement can be 1.8 volt. It's very difficult to program that, right? But Zener diode is a very good example, and the crux of this course is essentially trying to make something like a Zener diode. Okay, so the idea is, if I tell you that I give you an a priori information of this is how the load is going to change next millisecond or next nanosecond, then you can go and change this R, top R, to get the voltage just right. But as you will know that this is basically an impractical solution, right? We cannot really expect, you don't tell the user, you don't ask the user to constantly tell your phone that, okay, this is what I'm going to next, because even the user doesn't know what he or she is going to do next, right? So this is an impractical solution, which essentially means that you need some way of the circuit to sense how the output load is changing. Exactly. You need certain amount of feedback. You need some way of sensing how the output load is changing, and then feeding the information back somehow. We don't know how, we'll see. Somehow feeding the information back. No, I mean, I just took an example out of the hat. Let's say I'm assuming 1.5 volt requirement. If you assume a 1 volt requirement, then it will be 1:2, right? So whatever is the requirement, the crux of the idea is this division ratio, you need to keep it fixed. Okay, so if you need to keep the division ratio fixed, if the stuff on the lower side of the divider is changing, you have to change the stuff on the higher side of the divider also. And this has to be done on the fly. Okay, and since you don't have a priori information, all you have to do is to sense what is going on and feed that information back into this resistor divider somehow, so that things change accordingly. Make sense? Okay. So the crux, so essentially what I am getting here is that we are looking for in this course. So the goal is to make an on-chip battery. Why do I say the goal is to make an on-chip battery? It's because what is the property of a battery? Regardless of whatever load that you are subjecting your battery to, it retains the voltage. Okay. So the goal of this course essentially is to make an on-chip battery. But unlike the traditional battery that you see, which gives you fixed voltage, we will not restrict ourselves to a fixed voltage battery. So sometimes, as it happens, that you would want to drive a variable load. Let's say you have a variable load. This load can be R, L, C, whatever. A switching load, I don't care. There will be some load, and you have some source Vs, and each source typically comes along with a series resistance. You hardly ever get a source without a series resistance, because that only happens in ideal world and PowerPoint presentations. So you will have Vs and an Rs associated with it. Now the problem is, if this load changes and if I directly connect these to this will not work. So the goal is again to make the stuff in between, right? To make the stuff in between, so that regardless of the change of load or any other fluctuation for that matter, I get the output voltage to be whatever profile I need it to be. Okay? Make sense? Yes. Okay, regulator is an application, right? A regulator essentially is an on-chip battery. Yes, you cannot, right? So the idea is, his question is, how can you integrate a battery on the chip, right? You cannot integrate a battery on the chip. What you have is an off-chip battery. You have to take that information from off-chip battery and do something on the chip so that your output of the chip essentially behaves like an on-chip battery for this all practical purposes, right? So which essentially boils down to the fact that you need a controlled source. Why do you need a control source? Because you are depending on an off-chip. You are depending on a battery. You are depending on something to drive your variable load. It's a battery, a 3.3 volt battery or a coin cell battery is not a control source. It's an independent source. But here in this case, what we will be doing, we will be taking an independent battery or an independent signal, and then we'll be using it to drive some variable load, which essentially means that we would require some sort of control source, because I want to take this information that I already have and then feed it somewhere. Okay. So this is all very heuristic, very hand wavy right now. We'll again, from the next class onwards, we'll go into details of how to go about doing this. Yes. You said it, right? So with the examples that I gave, when I say that I take a battery, I take a battery or I take a signal, I am trying to drive something while keeping the voltage constant, which essentially means that I am trying to make a voltage controlled voltage source, right? So again, we'll come to that. There are different types of control sources: voltage control current sources, current control voltage sources, and 2x2, right? You have only two variables. One can control, one can be controlled. So you can take your pick. So ultimately, essentially what we are trying to get at here is that from whatever discussion we had till now, what we are trying to get at here is we are trying to make a voltage source, right? Okay. What is the other property of a voltage source? Let's say I have a good voltage source, right? So I have a box. I bought it from somewhere. I don't know what it is. All I know is a source. Okay. So how do I know whether this is a voltage source or a current source? I mean, these are the only two sources, right? Internal resistance should be as low as possible, right? With respect to what? So let's assume that I went to the market and I got a source. Okay. the folks in the market told me that this is a voltage source, but this is not an ideal voltage source, which means there will be some internal resistance associated with it. So this is RS. Okay. And let's say this is 1 volt or something. So I stick a resistance RL here, and I see that this voltage is 0.5 volt. Okay. So what can I imply from this? What can I conclude from this? Because this is black box. I don't know what's inside. I only have access to those terminals. RL is equal to RS, right? So let's say assume I connected a 10 ohm load, and I found that RS is, this is 0.5 volt. So one option is the guy in the market cheated me, or other option is that this RL is very low. Okay. So then I go and say that, okay, fine, let me see, before I blame anybody, let's increase this RL. Okay. So I increase this RL to, let's say, 1 kilo ohm. And I found that this is going close to 0.999 volt. Just a random number I picked up, right? 0.999 volt. Then what can I imply? What does it imply? RS is less, right? And then so from these two information, let's say these two plugins that I did, what is it that that I would like to take home? What is the observation? Okay, I don't know Thevenin and all right now. Yes, what? Oh, no, forget calculation. I have bought something from the market. I want to make my circuit work. I know RS should be, but is it? I mean, minimum with respect to what? Again, that's the question, right? Which essentially means that. Pardon? So which means that this stuff is working fairly well with a 1K load, but it's not working with a 10 ohm load. That's all that's what I can imply. That's what I can take home. So if I keep on increasing this 1K to 10K to 100K and so on and so forth, so I will see, what should I see? One. Right? So which essentially means that maybe for some range of loads, it's working as a voltage source. For a different range of load, it's not working as a voltage source. Now go back and think from the perspective of a designer who is trying to design this box. Okay, you know that you will never be able to get RS to be equal to 0. That's anyway always the case. You'll never be able to make RS to be equal to 0, which means that if you are designing a voltage source, like on-chip voltage source, let's say, what information would you want? What is the first information that you need? Pardon? Information about load. You need to ask your customer, whoever that is, maybe another company, or maybe your friend next in the next cubicle who is designing something, right? You need to ask, what is the load that I am supposed to drive? You cannot be expected to design a voltage source to drive any load. And let's assume that that guy told you that I want, my load can vary between, let's say, 10 ohm to 1K. Okay. From this information, what information will you take away to design your voltage source? Pardon? Louder. Which means? Okay, so there is a jargon here. When we say minimum load, we mean maximum current output. Sorry, when I say minimum load, we mean minimum current output. When I say circuit is loading, it means it's drawing more current. right? So here the worst case situation is 10 ohm or 1K. 10 ohm is the worst case, right? So which essentially means that I need the information that I am taking home is this RS. I mean, if I am the designer of this circuit, I need to ensure that this RS is much less than 10 ohm. Okay, so that is what I need to take home. Now let's step back and say that I have this 3-volt battery. I need 1.5 volt. And probably I have this 10 ohm load. Okay. So this is, let's say, R, this is R. What can you comment on the values of R with respect to 10 ohm? Okay, let me hear from somebody else. Can I draw any conclusion on the value of R with respect to 10 ohms? Given that I want around 1.5 volt. Much more, R should be much more than 10 ohms or less than 10 ohms? How many of you say much more than 10 ohms? How many of you say much less than 10 ohms? Okay, so as it turns out, you require much less than 10 ohms. Why? Because ultimately this 10 ohms is coming in parallel to this R. And if R is much more than 10 ohms, then this effective impedance looking in the bottom side is effectively 10 ohms, right? R parallel 10 ohm is 10 ohms, which means that if R is much more than 10 ohms, it will not be 1.5 volt, right? So you would want R to be much less than 10 ohms so that need R to be much less than 10 ohms because I do not want the 10 ohms to load my voltage divider, right? So I want this voltage to be set independently of what my external variable load is. Now the issue with this is, let's assume that I made it a 1 ohm battery, R equal to 1 ohm. With R equal to 1 ohm, I'll be able to satisfy from 10 ohm to 1K or even 1 meg or whatever. Output will be 1.5 volt. But the issue is you will be drawing how much current? Always. Three by 2 means 1.5 amps. All the time, regardless of you are using video calling, YouTube, Facebook, whatever, right? Your batteries typically that you see have like 1200 milliamp power wattage, which essentially means that about 1000, let's assume for the sake of math, let's assume 1000 milliamp power, which essentially means that it will last you less than an hour just to bias your circuit. You are not doing anything, you just bias, your battery is gone. So obviously you cannot use this voltage divider phenomena to as a good voltage source. Okay. Any questions? Okay. So what I'll do is, as I said initially, I expect you to be proficient in network theory and all. So I have a mini tutorial. It will not be graded. There are a couple of questions. I'll hand it over in the next 15 minutes or so. Do it and hand it over to the TS. We'll take a look at what the class stands. Okay. Okay.